So I'm going to list some numbers that form a pattern, and I want you to try and continue the pattern. What might the next two numbers be?
5.
Pretty straightforward, not a problem. Let's do another one, a little harder. What might be next? And yeah. All right. How about all right. Let's rock this. All right, so we've got to make it a little harder. What do you think it is?
15 and 21.
Wow. Holy crap. You guys are like rocking this. All right, so I just want to back up a little bit and then we'll. So first sequence of patterns, a lot of times we are used to seeing things that are in order. And these are just a jump of 1 each time. All right, we just keep jumping by 1. And the next two, I decided not to jump by 1, but to jump by 2. So over here, I'm going up 2, up 2, up 2, and so on. This thing, the next one did the same thing, right? It just started in a different place. Up 2, up 2, up 2. So if your brain was thinking that increase by 1, increase by 2, then your brain, and again, our brains are all different, have different experiences, looked at that, looked at that and said, oh, that went up 2. Oh, that went up 3. Oh, that's weird. Oh, that went up 4. Oh, I think I see a pattern. The next one probably goes up by 5. And if that went up by 5, I might as well make this one go up by 6. Not too bad. All right, let's try another one. How about 1, 4, 9, 16. And again, if you're on Zoom, feel free to type something in here.
The next one, 25.
Sure.
That was very.
What do you guys think online? 25? If that's 25, what's next?
36.
36?
Yeah.
Okay. And again, for any of these patterns, there are more than one way to think about them. So a couple ways to think about this last one. You might do it the same way we did the pattern above. To get from here to here, I could add 3. From here to here, I could add 5. From here to here, I would add 7. So why not add 9 and see what happens? That's one way to think about it. Here's another way to think about it. The first number is 1. The second number is 4. The third number is 9. The fourth number is 16. Do you see a relationship between the 1 and the 1, the 2 and the 4, the 3 and the 9, the 4 and the 16 that you could then repeat? What's the relationship between 3 and 9 that's the same as 4 and 16? Squared. Yeah, I'm squaring the position the number's at. So this next one's going to be 5 squared and 6 squared and so on. 2 different ways to think about the same pattern. All right, so with that, those 2 different methods, here's some information about that. When I do this green, oops, that's not green. That was my finger, promise. When I do the green method here, that's called a recursive formula. Okay, recursive. These monitors in the way, huh? Oh, this podium is too tall. I don't think I can squish them down. Oh, go down a little more. Hopefully I don't break anything. Better? So recursive, and this is supposed to be a 5 there, sorry about that.
The people on the screen see?
Yes, they see I hope they see what's highlighted here. You guys are seeing my whiteboard, right? Christian and Noemi and Lorenzo. Okay, cool. And recursive just means do this procedure over and over again. In this case, my recursive procedure is to add odd numbers. How many people that saw the 25 and the 36 were thinking that green method? Okay. A lot of us are really good at seeing that kind of thing happen due to our past life experiences. Not previous lives, but earlier in this life. I don't know about past lives. So the other method here, that is called let's call it today. Let's call it a closed formula. And I'll show you what I mean by that in just a second. But I want you to think this. What if I needed the 100th term in this sequence? It'd be easier to do the closed version than it is the recursive one, because the recursive one, if I need the 100th, that means I needed the 99th, which means I needed the 98th, so I got to work my way all the way up to it. But it was easy to notice at first. Okay. So the closed formula is where you have an equation. In this case, the equation would look something like n squared. And then I would add, where n is the position in the list. Right, first position, second position, third position, and so on down the line. So if somebody wants the 100th position, great, 100 squared, done. Sometimes we call that position the index of the value. So this position in the list, also known as the index. And we can write formulas for all of these, or we could write them in recursive notation. And I'm going to demonstrate those notations in a few minutes, but I want to do a couple more examples. I'm only going to give 3 numbers this time.
Be 16 and 32.
60 and 32. Okay. Anyone disagree? Have another idea? I have another idea. 4, 2, 4, 8, 14. What would be next? 22. I think that would be another way to continue this. Okay, let's go over thought process on this. Caddy, what were you thinking about when you did the top one?
Make sure that's how you got your. I got mine by like 2 plus 2, 4.
4 plus 4, 8 plus 8. Yeah, or you could say 2 plus 2, that'd be doubling.
Yeah.
4 plus 4, yeah. So one way to see this pattern is say, oh, what I think he might be just doubling this number. So I'm going to take the 2, I'm going to multiply by 2. I'm going to take the 4, I'm going to multiply by 2. I'm going to take the 8, and I'm going to multiply by 2. I'm going to take the 16, I'm going to multiply by 2. Totally valid way to look at that pattern. My brain was stuck in the previous kinds of problems where I was thinking that this went up by 2, and then this one went up by 4. So maybe I'll go up by 6. And then here I'm going to go up by 8. Both of these patterns explain those first 3 numbers. My point here is having 3 or 4 numbers enough to definitively say what happens next? And the answer is actually it never is. There are some patterns are more common to our brains than others, But for any pattern you give me, like 5, 6 numbers, I can find the obvious way to do it, and then I can find some other weird ways to continue it that logically makes sense. Right? In this class, I'm looking for the most obvious way to do something. Right? So I actually meant this to be what you saw there. So if I really wanted that, then what I should have done is given up through 16, and then it would be more obvious that we're doubling. Okay. All right, let's try another one. How about 2, 6, 18, 54? I think I got the 54 right. Yeah. You might need a calculator for this one or a piece of paper. Some of these require more than just thinking about it.
Two.
Yes. 162 is the next number.
486.
What's the next one?
486.
486 is the next one? Okay. Some days I can do that in my head. Today, I'm not so sure. So what led you there? Multiplying by 3 instead of by 2 like above. Yeah. So the way I started this, I said, okay, I'm going to take 2, and in my head, I multiplied by 3, and then I multiplied by 3 again, and then I multiplied by 3 again, and had to double check my brain, make sure I did it right. Wasn't quite ready to do that one on the spot, but thank you all for your help on that one. Yeah, we're just going to keep the multiply by 3 pattern. So there's lots of ways patterns can continue. Let's look at another one. And again, if these were new to you today, you're going to get used to them because you're going to see them in the book and you're going to see them in the homework. 1, 2, 3. What might be next?
I mean, ideally it would be 4.
Ideally it would be 4, but I want it to be a 5.
And 8.
You said 8. Uh-oh. Okay, and then?
13.
Yes. Oh my goodness, you're amazing today.
21.
21. Wow, you guys are just kicking butt. This is going to be the best pattern recognizing group I've ever seen. All right, so what the heck is going on here?
You added the 2 numbers.
Yeah, you add the 2 previous numbers. So here we took the 1 and the 2 to get the 3. And then I took the 2 and the 3 to get the 5. And then I took the 3 and the 5 to get the 8. And this is a very famous sequence of numbers. It has a name. It's found in nature in a few different places. Anybody happen to know the name of it? You want to zoom? Give you a hint, it starts with an F.
Oh, the big good.
Figaro, not Fib.
Something like that.
Something like that. It's Italian person. Yeah, this is called a Fibonacci sequence.
We were getting found in nature.
Yes, this is found in nature. So I'll show a couple places this is found in nature. So I can get this right. One of the first documented versions of this was, I think, a few thousand years ago or a couple thousand years ago, and it was a story problem about reproducing bunnies.
Oh.
Right.
That.
So this guy had this pair of bunnies, and he watched them reproduce. Now, at first they were bunnies, and they weren't reproductive yet, but a little time goes by, and rabbits, they don't need long before they can start reproducing. And he claims it was every month. After a month old, they could reproduce. So I'm going to write B for a pair of bunnies. And then those pair of bunnies, after a month, matured into a pair of rabbits. We could call them BB if you want, and then RR. Now, once they're rabbits, they can reproduce. So this pair of rabbits reproduced, and now they made a pair of bunnies, but those 2 rabbits are still alive and hanging out. So let's say, let's keep track of months here. Okay, so the bottom line is every pair of rabbits can make a new pair of rabbits. Okay? And the new pair is always male and female. But bunnies have to mature for a month before they can make new bunnies. So keeping track of months, I'm going to call this month 0, and this month 1, and this month 2. And what's going to happen next? Well, I can stick with green. This pair of rabbits is going to keep continuing, and it's also going to keep reproducing. So it's going to make another pair of bunnies. This pair of bunnies can't make new bunnies yet because they're not rabbits. So a month has to go by before they are rabbits. So now I'm in month 3. The original pair of rabbits is going to keep on living life indefinitely. But they're going to make a new pair of bunnies. This pair of bunnies here needs to mature into a pair of rabbits. This pair of rabbits is going to continue living their happy life, but they're going to contribute some bunnies. And this process is going to continue over and over based on those rules, that they have to wait a month before they can reproduce, and they'll always reproduce a pair, male, female. So this would be the 4th month. And so then over here, if we, so my table has months, it has a diagram of how the bunnies are reproducing, and then I just want to count the pairs for each month. So at first, there's 1 pair, and they have to mature before they can make another pair. So now over here, we have 2 pairs, and then over here, we now have 3 pairs, and then the next row, we are up to 5 pairs. And do you see the pattern I'm replicating with this bunny idea? Yeah, so this was like one of the first times in a written document somebody came across this sequence of numbers, and then other people realized, oh, this occurs in other places too. So some other places this occurs, and I'm not going to try and draw a picture of it because I'm pretty good with stick figures, but that's about it. So I am going to go to one of my favorite websites, Wikipedia. It's usually one of the first hits. So they're drawing the pattern out here in a series of rectangles. There's some cool geometry behind it. And if you connect the corners of those rectangles, you generate a spiral like a conch shell. So a conch shell expands in a situation like Fibonacci, where the radius is growing, and the radius grows in a way that matches Fibonacci numbers. That's one place it was seen in nature. There's some rearrangement things about it up there. There's the bunny thing I was attempting to draw, all kinds of wild equations. Oh, come on, show me the other cool stuff. You used to have it on here somewhere. Let's see. This page has grown since I've been here last. We don't care about all this other crazy stuff. It's pretty cool math. It's amazing. All this math is just based on counting things. People get PhDs just counting stuff. They develop all these wild ideas. Who cares about these ideas? Does this seem like who would waste their time with this? How could this possibly be useful? Anybody have a cell phone?
Yeah.
How many people like their cell phones? It's math like this that made the hardware in your cell phones work. And how do you think your phone always has a connection? What does it mean to be a cell phone?
Magic.
Magic. It's more than magic. It's science. There's these cell towers all over. And when you're close to one, you're getting a signal at that one. But if you're close enough to another, it picks up the signal over there. Well, where does it go from there? Sometimes it bounces around the towers, depending where you are. Sometimes it jumps on some kind of line, like a fiber optic line or a cable line or a phone line, and goes to wherever it needs to go. So cell phone technology is related to this. Cell phone design is related to this kind of math. All the things we love and are addicted to on our phones. Okay, it's not showing me the picture I wanted. Oh, there we go. What does this look like here? It's a flower. Yeah, so this is a yellow chamomile head, but a lot of flowers where the seeds extend out in a pattern, that pattern is Fibonacci. There'll be a central seed and then 2 next to it and then 3 next to that and 5 wrapping around. So the Fibonacci pattern lives inside the way these crazy flowers have these multiple seed pods, which is pretty neat. And there's a ton of other examples if you dig about Fibonacci. And that's one amazing thing about math. There are so many interconnections all over the place. Okay, next, we need to do some notation on the kinds of sequences we've played with, and I want to categorize them a little. So we're going to back up to the easier stuff. So the first type of sequence I want to go over in detail is called an arithmetic or arithmetic. In an arithmetic sequence, the numbers are the same distance apart consecutively. So examples of arithmetic sequences we've seen so far are 1, 2, 3, 4, 5, and so on. 2, 4, 6, 8, 10. 1, 3, 5, 7, 9. And we actually looked at one earlier in the previous section. 3, 6, 9, 12, 15 would be one also. And all of these sequences have the pattern that consecutively means in order, they're the same space apart. Okay. That spacing, that distance, we usually call it d. So for the first one, d equals 1, the distance between the consecutive numbers. Next one, d equals 2. This one, d equals 2. This one, d equals 3. But any distance we want in there. How about this one? 1, 4, 7, 10.
D equals 3.
D equals 3 again. I just picked a different starting point. So to describe an arithmetic sequence, you need to name 2 things: where to start and what's the distance. And then that's the pattern. That is that it's encoded. Now this goes on forever, right? But we can encode it with just 2 pieces of information. We say it's, or 3, I guess. We say it's arithmetic, we say the distance, and we say the starting point. So to describe this last sequence right here, I could just write in words, start at 1, increase by 3. That would be just a brief statement sentence that says how to generate this set of numbers. Now, in math, unfortunately, we like formulas. So we're not going to do much algebra in this class, but we're going to do a little tiny bit. Today is going to be like the most algebra we do on any day in the future of the course. So I'm going to call this right here sequence A. And sequence A has a first term of 1. Sequence A has a second term of 4. Sequence A has a third term of 7, and so on. So I'm using subscripts to indicate what position in the list I'm looking at, right? Using those subscripts is kind of like, do you remember in an algebra class using function notation? So this is a lot like function notation, and I'll show you just in a second. So to describe the sequence, I would say start at 1 would be to write A1 equals 1. And there's 2 ways to say increase by 3. I could just say d equals 3. But typically what we do is we write something like this. an plus 1 equals an plus 3. So what do the n's and the n plus 1 mean? Well, remember before I talked about the position we are in the list? Like, use red, the first position and the second position and the third position and the fourth position and so on. We refer to the position with the letter n when we're talking about sequences. So anywhere in this chapter, if the letter N pops up, that means we want the nth position in the list. Could be the 10th position, could be the 100th position. Okay. That's also called the index of the list. So what this says is to get the n plus 1, that's just the next position. Look at the previous position and add 3, is what that says right there. And when we use this kind of notation with the subscripts, this is what we call recursive notation. Using the subscripts. It's great. It describes what we naturally see. Add 3, add 3, add 3. But there's other ways to look at it, like this is a pain to get the 100th one. Okay. So in that case, I would somehow like to turn that into a formula where I can just plug in 100 and out pops the answer. So let's pick that up on the next page. So we have the sequence 1, 4, 7, 10. Recursively, just summarizing what we already did. We know we could say that's A1 is 1, AN plus 1 equals AN plus 3. And to just use that notation before I move on, A1 is 1. A2, well, that would be my n plus 1, is equal to A1 plus 3. What's A1? Well, look up, it's 1, right? So 1 plus 3. So I'm using this right here to generate more terms. A3, that's my n plus 1. A2 has to be on the other side because it's 1 less, or 3 is 1 more. And then we add 3. I forget to write the answer. 4. So this means take 4 plus 3 to get 7. Usually, I think this, but don't write it. Because I'm giving it here. I'm writing explicitly just because you probably haven't used this notation before. Keep going. The fourth term, oops, wrong color. A4 is going to be equal to A3 plus 3. 7 plus 3, which is 10. Now, just back up for a second. What was A3? Well, wasn't that A2 plus 3? So just kind of sneaking in here, this right here can be expanded as A2 plus 3, and then I have that plus 3 right there too. A2 was really A1 plus 3, and then I have those other 2 plus 3s tagging along, and A1 was just 1. So another way to think about this when I put it all together is A4 is going to have to be a 1 followed by 3 3s. Did I really need all that notation to do it? No, but there are some harder problems that I have to have that notation for. We'll get to that in a minute. Really, I could just look up here and write down what I was thinking. Add 3, add 3, add 3, right? To get the 10, I have to start at 1 and add 3 times. So I'm going to put this in a table to simplify it a little bit more. I think I need to sneak the table over here. So I have n and then a sub n. So we've got the first term is 1. The second term is 4, but the 4 came from a 1 and a 3. The third term is a 7, which came from 1 and 2 3s. Getting used to this new pen. 2 times 3. And the fourth term came from starting at 1 and adding 3 groups of 3. The fifth term, what's the fifth term going to be? 1 plus how many? 4 groups of 3 to get, let's see, we don't have that up there yet, but that's going to be 13. Now I'm going to make a big skip here. I'm going to skip on down to the 10th one. The 10th is going to be a 1 plus how many groups of 3? 9 groups of 3, right? It's always 1 less. Why 1 less? Well, because we started at 1 and then we start jumping after that. We don't start adding 3s till after the first term. So it's always going to be 1 less 3. All right, what about to get the 100th one? That's going to be a 1 plus how many 3s?
99.
99 3s, nice. Okay, here's where it gets more exciting. I want the nth one. Starting at 1, how many 3s?
N-1.
Ooh, you're on fire. Yes, there will be n minus 1 of them. And it turns out all of these sequences, arithmetic sequences, behave the same way. So I'm just going to summarize it and then we'll test it out on a different sequence. So 2 powerful formulas here. 1 is this recursive formula, and 2 is this one right here, which is a closed formula. Instant gratification. We can get to the 100th term or the millionth term easy. That's called the closed version. All right, so our arithmetic sequences. So we either have the first term, often we just call that A, and then we have an plus 1 equals an plus whatever the distance is. I'm just going to call the distance d. Could be 3, could be 2, could be something else. That right there is the recursive version. You can always use the recursive version to get the closed version. So for the closed version, we'll say a sub n. It's going to be start at the first term, a or a1, either way. And then we're going to add a bunch of d's. How many d's are we always going to add?
N-1.
Always 1 less, because we have the first term. So this would just be an n minus 1. And this works for any sequence you recognize as arithmetic. Yep, it's backwards up there. I'm going to put up another sequence and see if you can come up with the closed version of it. How about what I want you to do is figure out the next couple of terms, write them down on paper, and then see if you can come up with the formula to get the 100th one. Call this sequence B. This one, right? We would start at 7. And what are we adding? 4. So then we would add on to that n minus 1 4s. So then I can use that to get the 100th one, which would be 7 plus 99 4s. I don't trust myself doing that in my head today. $403? Oh, wow, I like it. So the first one is 7, second one is 11, third one's 5, fourth one is 19, The fifth one, add 4 should be 23, add 4 should be 27. Fifth, sixth. And the 100th one should be 403. You've done this before, but it looks different. Connection to previous math. Do you remember y equals mx plus b? And sometimes it was written with function notation like f of x equals mx plus b. Oops, it's the letter there. What was m? The slope, right? And the slope described how it increased. Well, that's what our d does here. What was the b? The y-intercept. What is it? What is x at the y-intercept? 0. Do we have a 0th term here? Could we sneak in a 0th term, something right before 7? What would it be? Well, this is going up by 3 in this direction, or up by 4 in that direction, so we'd have to go back by 4 in this direction. So 3 would be the 0th term. So if this really is like a linear function or a line, then I think this should be like the same as y equals 4x plus 3. If I go back and think about a 0 term, something right before the first one, which would be like a y-intercept. Let's see, does that work? What happens if we plug in 100 here? 4 times 100 plus 3, holy crap, that's 403. So it turns out that's a slightly different way of thinking about it. I'm using this other recursive notation because we're going to use some harder problems. Okay, I got to do 2 more quick examples, and then we're going to look at the activity for this week, where we're going to play with some blocks. So arithmetic sequences, there's a bunch of practice on this in the homework and examples in the book. Geometric is the next big one. We've already done 2 examples of geometric sequences. One of them was 2, 4, 8, 16, 32. The other one was, let's see, I believe it was 2, 6, 18, 54, and something else. 162, I think, calculated. And what geometric sequences do is they don't have the same distance apart, but they're the same multiple apart. So geometric sequences have a common multiple for consecutive terms. And if we think about these recursively with the idea we had with linear, it's only a slight difference. So with the first one, let's say that's sequence A this time, I would say A1 is 2, so start at 2, and then multiply by 2. To do that, I would do something like AN plus 1 equals AN times 2. And that describes how to keep generating new numbers. For the next sequence below, let's say that's sequence B, the first term there is 2, but this time to generate new ones, Bn plus 1 would be Bn, the term before it, times 3. But that's great, right? I can keep multiplying by 3 in my head over the calculator, but when it comes to getting the 100th one, I do not want to do that 99 times. So just like there's a shortcut for the linear, maybe there's a shortcut here. So let's see, with the linear arithmetic, repeated addition became multiplication. With the geometric, repeated multiplication is going to become starts with an E, X, P,
Exponent.
exponents. Yeah, repeated multiplication is an exponent. Okay.
You said X, I wrote X.
So let's consider sequence, the second one, the B's. So N versus B. So at first, I just have a 2. And then my next term is 2 times 3, which is where we get the 6. And the next one is 2 times 3 times 3, or 2 times 3 squared. And that's going to give me the 18. And then the next one after that is going to be 2 times 3, 3 threes, so 3 to the third power, and so on. So then might I be able to guess if n equals 10, then I'm going to have 2 times 3 to what power? The 9th power. Yeah, kind of like before, but it's a power instead of a multiple. And then if n was equal to 100, 2 times 3 to the 99th. And what if we just let n be n and we don't give it a value? It would be 2 times 3 to what power? N minus 1, like before. Yeah. And this system, this pattern works for any geometric sequence. The common multiple is usually given the letter R. It's R for ratio, because if you divide these numbers in pairs, 6 divided by 2 is 3, 18 divided by 6 is 3, 54 divided by 18 is 3. In pairs, the common ratio is, that's why they call it R. Oops. So the general formula is always going to be the first term times R to the power n minus 1. Always going to work out that way. And then boom, you can get any term you want. All right, last example before the toys. Other stuff. Sometimes sequences don't fit an easy pattern like arithmetic or geometric. So a couple of examples of other. Fibonacci, I believe, falls under other. So usually I started the Fibonacci with a 1 and a 2, but usually people start it with a 1 and a 1, and then a 2, and then a 3, and then a 5, and then an 8, and so on. If we call this sequence F, then to get this started, we need the first 2 terms. So we would have to say F1 is 1, comma, F2 is also 1 for this version of it. To get new terms, Fn plus 1, we have to add the 2 previous terms. Well, right before n plus 1 is Fn, and right before Fn would be Fn minus 1. Oops. Can't write little dashes apparently on this whiteboard. So this is just the recursion shortcut formula that says add the 2 previous terms. There isn't an easy closed formula for this. We're not even going to go over it. It would take me like half an hour to do it. I don't want to go there. This is way easier. And the other ones, the recursive was nicer. And this one, I'm sorry, the closed was nicer. And this one, the recursive is nicer. Remember this sequence, 1, 3, 6, 10, 15. We found that the pattern there was up by 2, up by 3, up by 4, up by 5. Okay. And just notice each of these goes up by 1. We saw a similar version of this with the sequence 1, 4, 9, 16, 25. This went up by 3, and then up by 5, and then up by 7, up by 9. And the bottom sequence went up by 2 each time. This is called the method of common differences to see if you can generate the pattern. And sometimes I did 2 rows of differences. Sometimes it takes 3 or 4 rows of differences before you see how to continue. Okay, I'm going to skip those for now. When there's 2 rows of differences like this, where you get finally a fixed number, these are what are called quadratic equations. And we'll look at those more in the homework. And the book has a couple of examples of this, but I'm going to stop there. I'm not going to go over that closed form because the method of differences lets you continue. So we could easily get up to the 10th term. I would never ask you to do the 100th term for one of these. Right? I would ask you to do the 10th. I think that's within our capabilities. All right, toy time. Or actually, it's stand up and stretch time, and then it's toy time. So take a quick break. We've been going at this for more than I usually want to. Or come and ask me something.
Yeah, because I also.
Okay. Oh, you're already on it. Nice.
Yeah, no, I actually already did the thing that I
Cool.
realized I originally did one well.
Okay.
I originally had 62,
Okay.
but I did 185 times back and forth. So it was like one thing all there.
Okay. I gotta look at the color picture to get what you're doing. All right. Okay, so this one right here. Okay. So I'm going to bring up pattern block or actually no, I'm just gonna so the other one. Say that again.
I think I realized I needed to do 3, not 4.
How come?
Because I didn't realize that one was there.
Yeah, it's the same one. Yeah. So yes.
So it'd be 61, 61, and then, well, this one would be 62. Because it was one extra if I did 3. If I had 585 divided by 3, and there was an extra, would it be the.
It would have to be the next hexagon.
Okay.
Yeah. All right, cool. You figured it out. So you're still in the room and you didn't stand up and stretch, then come stand up and grab some of these. And you'll need a few of each, at least 3 of each type. Yeah, absolutely. Yeah. And you don't necessarily have to resubmit the whole thing unless that's easy to do. You could just resubmit a correction of one part. Okay.
And I'll just go like this.
That's cool.
You know it's
Thanks for playing, Caddy.
She posted it on PTO page on the chamber. The old one, and she also posted that it's September 17th. Everyone's messaging me. It looks like they posted it from the elementary school.
Let's get back at it. So we're going to take a look at the second activity, activity 1-2. And to do so, you have a couple options. Anybody could use the virtual pattern blocks or pattern shapes that I have here. I prefer to use the real ones because it's fun to put my hands on stuff. Anytime you bring toys like this into the classroom to do math with kids, you got to budget a few minutes to screw around. Right, so they're going to make fun shapes. They're going to stack them as high as they can. Anything that they can think to do, they're going to, and just let them mess around. Playtime is super important in any subject. We are going to use these pattern blocks to make sequences where we show how the sequence grows, and then we want to just make predictions about what this is going to be like in the future. And so for those predictions in the future, I'm going to ask questions like, make the next, kind of like we were doing with just the numbers on the page. This time we're doing these, like, what's the next one going to look like? In the 10th one, how many squares are in it? How many hexagons are in it? In the 77th one, what's going to be at the end of it? How many of each pattern block are in there, and how do you know that? Okay. Now, when I was doing the regular number sequences, I made tables almost all the time to keep track of stuff. Sometimes the tables are vertical, sometimes horizontal. In the beginning of class, when I was playing with the coins, I made a table to keep track of stuff. There were a few problems last week where I made tables to keep track of stuff. Anytime I'm counting stuff, a table is super helpful to help me organize my thoughts. So I highly recommend for each of these problems, you make a table. So I'm going to skip the first one because that's the easiest one. And I'm going to get started with you on the second one. And then I'm going to get started with you on the third one. And then you can finish it on your own time. It's not due to the end of the week. I just want to get started. So we're going to jump to pattern number 2. So I have a picture of the first view here. Let me blow this up a little bit. Ooh, I don't want to watch the video. There's also a video of me doing this with others in the past. So what I would like you to do, I have the first, second, third, and fourth, make the 5th figure. And if you think it might help, make the 6th one too. And then I want to use these figures to make a table to describe what we see. Use my toys to do this on the side here. Not the way. Wrong here. Oh, I hit the wrong button. Okay, reset. That's what I want. gonna bring my virtual one in here. And one cool thing about the virtual one, you can replicate stuff. So if I click and then hold shift, I can get a bunch of them. And then I can duplicate them and tag them on there. All right, so let's see. This would be 1, 2, 3, 4, 5, 6. Okay, that's too many. Oh, actually, I know what to do. I was thinking I wanted the 5th and the 6th. Get all of these, duplicate. Just get rid of that. There we go. Okay, so this is what the 5th one should look like, right? And then this is what the 6th one should look like. So what we're going to do is we're going to make a table for these. So to do that, I need this one in there. Page. I need one button. This one in there. And the others. Right. And I think seeing the 6th, we can easily project to the 7th. All right, so here are my terms. All right, so what do I want to keep track of in my table? As much as possible. So I want to know which figure I'm on, so we'll call that N. I'm just going to put an H for hexagons. What is that red shape called? Anybody know? A trapezoid, yeah. So T for trapezoid. How about the blue one? A lot of names is the best name for it. It's a quadrilateral, but it's a special quadrilateral. Parallelogram, but it's a special parallelogram. Starts with an R, H, O, M, B, rhombus. There we go. It is a rhombus. So I want to keep track of how many hexagons, how many trapezoids, how many rhombuses as I go. Now, fortunately for this sequence, the total number of shapes is the same as the position I'm on, so that's pretty straightforward. So the first has 1 hexagon, no trapezoids, no rhombus. The second figure has a hexagon, a trapezoid, no rhombus. The third figure has a hexagon, trapezoid, and a rhombus. And I'm just going to keep going. Fourth. Now I'm up to 2 hexagons, a trapezoid. Oops. 1 trapezoid. 1 rhombus. Fifth one. Struggling to draw 5s on this new whiteboard. I'll work on that. 6th one. 7th one we didn't draw, but I know that I got to get another hexagon in there because that's the pattern I've seen. I'm hoping you guys see the same pattern. Just going to put a couple more, and then I'm on a room. All right, so there's not much other information to keep track of here. And then I asked some questions related to this. So let's look at the questions that I asked. All right, so we're almost at the 10th figure, so we can easily add to this for the 10th one and say what's going to come next. I'm just going to squeeze that underneath. The 10th one is going to have to jump up on the hexagons. How many hexagons are in? Oop, not going to have 10, sorry. It's going to have how many? 4. That's better. Now, I'm asking about the 185th. ooh, that's pretty far down. Every once in a while, when something like that seems too big for me, I just pick a smaller number and play with it. Like maybe I could try the 15th if 185 seems daunting. But there is a pattern going on here. How often does this pattern make a major jump? Every three, right? Every third one, it just starts over with a hexagon, a trapezoid, and a rhombus. So groups of three is super important. Isn't every third number divisible by three? Right, so we got that going for us. So shouldn't I be able to figure out how far away, well, maybe 185 is a multiple of three. Anybody know the trick to see if some number is a multiple of three without actually dividing? Remember learning that in school once upon a time? No? Okay. I'm not going to spoil it. We'll talk about it later. I can just divide 3 into 185 and see what happens. Okay, so whip out a calculator, take 3 into 185, and what happens? Yeah, just do it here. 3 goes into 185. 3 goes into 18 6 times. No remainder. 3 goes into 5 once with a remainder of 2. So I think that means the next number must be a multiple of 3. Right? 3 goes into 186. 3 goes into 18 6 times. 3 goes into 6 twice. Yeah. So 186 must have 62 hexagons, 62 trapezoids, and 62 rhombuses, right? Because that's what all these other multiples of 3 had. And the 185 must be like the row before each of those. So the 185 has to be kind of like the way 2 was, or the way 5 was, or the way 7. Oh, no, 8. Undo, try again. 8 was. Okay. So based on the division I did there, see if you can come up with answers for 3 and 4. Write something down and then compare with somebody else. If you're on Zoom, feel free to get bold and try typing something into the chat. You know, that's kind of scary. And you should be able to chat to each other too, instead of the whole class. So that's an option also. Which pattern blocks are going to be at the ends of the 185th one? My claim is the 185th one is like the second one, the 5th one, and the 8th one, because it's right before a multiple of 3. So what do the 2nd, 5th, and 8th ones have in common? I don't have 7 or 8 up there. We can imagine. Easy question. What does the 185th start with? What do they all start with? Hexagon. Oh, shit. Hexagon. Okay, so sometimes like these are an easier question you can ask to fulfill the whole question. All right, so for sure we can say, hey, the 185th starts with a hexagon. What do we think it ends with? What did the second one end with? What did the 5th one end with? Okay, and the 8th one is probably going to end with a trapezoid. Is that true? Let's go see. In the 7th one, we had 3 hexagons, 2 trapezoids. In the 8th one, 3 hexagons, 3 trapezoids. So we just added a trapezoid there. Yeah, so the 8th one's going to end in a trapezoid. So I'm pretty sure the 185th is going to end in a trapezoid. Cool. Yeah. Good. Write that down as a sentence. You've answered question 3. Question 4 wants you to explain how many of each are going to be in the 186th. Which means you also have to tell me how many of each are in there. And it's on the screen in symbols, but not in words. You got to put it in words. So write something down. And then check with a neighbor. If you're on Zoom, type it in the chat to somebody or the rest of us. As scary as that is. At least it would have been scary for me as a student. There's lots of ways to word those. So for number 3, I'd probably say something for which pattern blocks are the ends of the 185th. The 185th starts with a hexagon and ends with a trapezoid. And it didn't ask why, so I don't have to say because there, so I'll skip that. The next one asked why. Okay. The next one, how many of each pattern block, explain how many of each pattern block are going to be in the 186. So first thing I should do is say, well, 3 goes into 186 62 times, so there should be 62 of each. Why? Well, there's only 3 shapes, so every third time through, we get another group of the 3 of them. Would be one way to say it. Lots of other ways to word it. Because we're repeating something every 3 times, division by 3 turned out being important to predict the future. Now, for those of you on Zoom, if you happen to like Google Docs, screenshots of these toys in Google Docs go really good together if you wanted to type up this. This is not something that needs to be typed up. It could be handwritten notes as long as your notes are neat and readable by me. So you can either snap pictures of any written work that's neat. If you really struggle to draw those, and some days I really do, right, I might resort to screenshots and having a Google Doc with some screenshots. But with a little practice drawing these isn't too bad. All right, I'm going to take a look at the next one. And something that's super important, we meet once a week. In between, if you're stuck on something, you should write to me. Right? So if you're writing this up later to submit and you're not sure about one of your answers, write to me. Now, I usually don't give direct answers to things like this. I'll talk about a similar problem to help point in the right direction. All right, we're going to look at the third one. You guys are going to do the fourth one on your own. And I just snap a picture of this. New page, please. And then that's all we're going to do today. All right, so let's see. Draw the fourth figure. Couple options. You have the toys there. You could grab some more triangles to make the fourth figure, or you can attempt to draw this on a piece of paper. I'm going to try and draw it on a piece of paper here. Digital paper today. Okay, let's see. For the fourth one, oh, I should draw it in green. All right, And then it's going to have triangles going up like this. And then another row on top of those. Top of those, and another one on top. It's not too bad. I'll take that. Just going to highlighter to color them in a little. I'm only concerned about the green toys. The white space in between is irrelevant. So this is the best of my artistic ability today, the fourth figure. Okay. How many green triangles are in the 10th figure? Okay, so now I think I need to make a table. So I'm going to make my table go vertical. Think about the 10th. There's a couple questions about the 10th and a question about the 100th. So N versus triangles. All right, the first figure has one triangle. The second figure has three triangles. The third one has six. The fourth one has 10. Oh, that looks familiar. Have we seen that sequence before? We've actually seen this a couple of times. I'm not gonna draw the fifth one, but I think I'm ready to state. What is the fifth one? How many? We need to add a row of how many in the bottom of the fourth one to get the fifth one? Oh, I'll re-explain what I'm thinking. When I made the fourth one, what I was thinking is I just needed to add some triangles underneath the third one. I added four of them. So how many are you going to add under the fourth one to get the fifth one? Five, yeah. So five more is going to give me 15. And we saw this pattern earlier in class. Plus 2, plus 3, plus 4, plus 5. So I can keep generating that till I get up to the 10th one. I'd rather not do that one step at a time up to the 100th one, but I could. This is actually like something we looked at last week. I'll give you a hint. Hi, Lorenzo, can you hear me? Hi, Lorenzo, my name's Gary. And Lorenzo and I walk up to each other and we shake hands. And then I go over here, hey, Sam, I'm Gary. Yeah. Right. Remember we did this last week? That we had the introduction problem versus the handshake problem. My claim is this is like the handshake problem. And I wrote something like this in my notes. It wasn't called triangles, it was called handshakes from last time. I'm going to redraw this in a slightly different way. I'm much better at drawing little circles than triangles, so I'm going to draw this with circles. So here's my first one. Here's my second one. Here's my third one. Here's the fourth one. And I could keep going from there. And then just for fun, I'm going to turn these into triangles. Then I'm going to make a little kind of hint to go with it. Sometimes it's nice to turn triangles into rectangles. Let's try that one again. Okay, this new diagram is a hint on one way to solve the problem. I had a hint in the last class on my notes on how to solve this. This hint leads to a formula where we can just plug in 100 and out pops the answer instead of having to go 1, 2, 3, 4 all the way up to 100. Okay. So I'm going to stop there and leave it at that for a minute and let you struggle for a little bit. And then if you get really stuck on it later in the week, feel free to write to me and say, okay, here's what I tried. Not sure if it's right. And then I'll give you some feedback on it. But you got to give me something. You got to show me something you tried. You can't just write, I don't get it. Okay, so you got to try something. Okay. So recap here. We are working on, where'd the book go? Over here. Section 1-2, exploring patterns. So if you didn't already do the reading exercise, jump in, read the section, and then I want an outline that's numbered automatically with comments underneath about what each of the topics is about. It's up to you on how much you want to include. I have some people that just write one sentence under each. I have some people that like to write a lot of stuff. A lot or a little, as long as there's a little bit and you're correct. Start working on the homework assignment if you haven't already. It's problems like the ones we did in class where you're trying to come up with formulas. And oops, too far. And then the activity, we pretty much did one together, number 2 together. We got number 3 started. In comparison, number 1's pretty easy compared to number 2. So keep working on that. It's not due to the end of the week. Oops, how come I'm on the page? We're on that page. Don't forget, there's a videos page there with videos about similar problems I've done with people in the past. Some of them are with other classes. Some of them are just me talking to the people in the future. And if you get stuck, get in touch with me. Super important. All right, you can just drop the toys in the bin on your way out. If you're online, hang out if you have any questions. I'd be glad to take more questions. Otherwise, the class is over and you're free to go get dinner or take a walk before the sun sets. So it doesn't need to do. You're welcome. Have a good day. What's up, Angelica? Does your mic work? Can you ask a question? Oh, that's a bummer. Okay. Yeah, so online tutoring, there's a couple of options. One is making an appointment with me. So if I go to, let's see, the syllabus here, I have a link to my regular office hours. So if you send me a message when you want to meet, if it matches one of these times, then just let me know which time you're going to be there and I'll make sure I'm on Zoom. Here's the office hour Zoom link here. If those times don't work for you, then check out my weekly calendar and message me and suggest a different time to meet. and I'll be glad to meet with you and go over some stuff. Otherwise, I'm probably the best tutor for this class. There's BrainFuse online tutoring you can try, and then there's the Math Cafe tutoring, which I usually have a link in my course, but did I see it in there? I'm gonna have to go look on the BNCC website for that one. They did not list the Math Cafe there. Okay, so let's go check out the Math Cafe. Tutoring, cafe. And they have a person in Hermiston and a person in Pendleton. And let's see, the hours are usually listed down here. So let's see. Yeah, so if you can't get a hold of me, this is another option. I'm going to add that to the syllabus. Did you want to try and meet tomorrow or Wednesday? And does 9 or 2 work for you, or do you want to try for a different time? Wednesday? What time? Let's see, Wednesday I have 2. That works otherwise, or let's see. On Wednesday I don't have 9, I have a class then. Let's go check out my calendar. Wednesday, oh, how come 2 isn't on my calendar? That's weird. I have class from 9 to 11, 11 to 12 Wednesday. So I could do after 12. Oh, let's see, I have another meeting. Schedule is not up to date. That's bizarro. I swear I updated it. I believe I have a 3 o'clock meeting. So I could do noon or 1, I'm pretty sure. Would either of those work for you? Noon? Okay, so let me add you to calendar. Calendar. Oh, tutoring's listed there. I wonder why it didn't appear in the other one. Interesting. Figure that out. Noon. Yeah, picking up the kids is important. All right, I got you in my calendar. So all you'll need to do is go to the syllabus and then just click the appointment Zoom link. Then and if I'm not on immediately, that means my class must have been asking questions after, but I'll be there soon. Okay, sounds good. Yeah, it'd be good to talk when we're on Zoom together later. All right, have a great night. All right, I got to sign off now, Noemi. Have a great night.